All right, our group project is the Automated Cat Feeder Plus. Our team consists of me, Sam Michelson, Bradley Estacio, and Carlina Veller. In this presentation, we're going to be going over some of the ideas considered, the project overview, hardware and software aspects of the project, technical challenges, and a timeline. So some of the ideas considered beforehand were one of which was a plant-sustaining terrarium, which would basically emulate some sort of non-Midwestern climate to habitate some kind of plant. And then the other idea was a split flip display board that would display more than just characters, could display colors, and you could do some cool artistic things with it. But ultimately, we did end up going with the cat feeder. So here are some similar products that you can find online. Obviously, you got like the simpler design up top there, and then the more sort of advanced ones on the bottom right that we're kind of trying to take inspiration from. So as many of you know, especially those of you who have pets, more specifically have cats, you're aware that other than providing them with cuddles and affection and all that good stuff, one of the only really responsibilities you have with them is to make sure that they get fed. So oftentimes people, especially people who are busy, who will be gone for extended periods of time, what have you, they'll leave their cat just extra food in the bowl, which is not an ideal solution because a lot of cats, not all cats, but a lot of cats will just kind of listen to their instincts and finish whatever's in the bowl as soon as it's there. And this can, in some cases, lead to cats overeating, becoming obese, and just, unhealthy in general. So we wanted to create a system that basically solves that issue and allows users who are very busy, who aren't home, to make sure that their cat gets fed and also gets fed a healthy amount. And in addition to making sure that the cat is fed at a proper time and fed an adequate amount, we also wanted to deliver some more advanced features and also engage with the pet a little bit, which is where the laser toy module comes in and the attached camera module comes in to allow users to see their cat, check in on their cat, see if the food is being eaten, and also play with their cat with the laser toy.
So our idea is an automated cat feeder. Our design was to create something fun, not only for the pet, but also for the user, so that while it was in their house, it didn't look crazy, but, was somewhat modern. We wanted to make sure that it was airtight to prevent smell leakage, because one of the worst things about having a cat is the smell of the food. We also had the idea of using a paddle wheel to push the food out of the design to the cat. And we had a few ideas of things to add onto the basics of the cat feeder, such as a laser to play with and the camera to see what the pet is doing, which I will now go into detail about. Going on to hardware, we have our first main component of our product, which is our feeder aspect. So at the bare bones of it is a stepper motor. So a hybrid stepper motor has a 1.8 degree bipolar step in the motor that allows precise repeatable steps in movement, which we thought would be important for making sure that the right amount of food is coming out at every part of the day that it is scheduled. So with this, we can make sure instead of just sending 5 volts in, it's, turn it 30 degrees, for which we will figure out during our trial and error of our project. We also wanted to use the design aspect of a cereal dispenser for dispensing the food out. So if you look carefully, you can see the paddle wheel. So inside we will put the motor, and then as it spins, it'll be an exact amount. Next up, we have our camera and our LCD display. So with the camera, it has a fixed focus lens and a small socket on the board, and with dedicated CSI interface, which is perfect for our project. The camera supports up to 3280 times 2464 pixel static images, which again is just what we need because we don't need high quality photos. We just need to know the content of the bowl. With this camera, we can view if the cat is eating, if too much food is coming out, if too little is coming out, or if nothing's happening at all, which could be useful later on in the product development if, let's say, we're outside of where the device is, so we know we can fix it right then and there instead of having to go on location. Next up, we have what I'm personally most excited for, which is the laser toy module. So for our product, we wanted to make sure that it wasn't only, just something that you could have at home, but also play with your cat while, let's say, you're at work. And so with this laser toy module, it has 2 servos attached to it, so it can move up and down, left and right, so we could draw circles. And what's better fun than playing with your cat? We also attached a manual switch because we thought it would be important to make sure if the laser was overheating that, we just had a quick fix, but it's not just, unplugging the system and plugging it back in. So to go into more detail on that, since the Raspberry Pi does not have a lot of PWM pins, we're going to be using a fully dedicated PWM driver chip on board to both control motor direction and speed. And the chip handles all the motor and speed controls over I2C. There's only 2 pins, SD8, SCL, that are required to drive the multiple motors, and since it's I2C, we can also connect other I2C devices or hats all to the same pin. Our default address is 060, which can be offset with solder on contacts on both rear. Next up, we have a Raspberry Pi Model 4B, so we just wanted to show a schematic of what we will be using in communication. So it's the newest Pi. It has dual band, all the fun gizmos and gadgets. Its Bluetooth is 5G, so it is the most recent. And then the GPIO pins are used for controlling all of our equipment. Finally, we have our circuit design. So if you look on the left, you could see our overall big picture design. So you have the device in the middle with the paddle wheel, which has the motor connected, which would release the food. You have the camera, which would go on the underside of the device to look down at the food content. And then you'd have the LCD, which would be attached somewhere on the product so that it's visible, but not like too obvious where the cat gets on it. And then we wanted to attach the laser module on top of it so that it was discreet where the cat wouldn't play with it once it figured out what the laser was, but had the highest vantage point when playing with the cat. And then on the bottom, you could see our Raspberry Pi connected to our circuit board and our power, and then our power adapter, since we have multiple components that are using different types of power.
Now we will be moving on to software components of our project. One of the main software components that we wanted to implement in the project was a mobile app. This will be developed in Android Studio. This will ask the user to sign in. Signing in will give the user a menu with several options to choose from. One of the most notable features to point out are setting the feed times, set 2 to 3 feedings per day. Looking at the feeder log, in which shows the user past 30 days of feedings. Viewing the camera, possibly on cat or levels of the food bowl, and not pictured on the sketches is an option to activate a laser. Of course, the user can also check the current feeder status, it will let the user know if it is offline or online. And we are also giving the option to activate outside of scheduled feeding time if they choose to do so. When it comes to interacting with our hardware components, such as the stepper motor, we the Adafruit MotorKit library, which contains several other dependencies, Python, that will allow us to easily communicate our stepper motor. As mentioned in the mobile app slide, we'll have a camera connected to our Raspberry Pi. We can use a interface such as PyCamera in Python to allow communication between the Raspberry Pi and the camera. With this, we can record to a network stream, output it to some media player. In this case, we want it to be our app. On the enclosure itself, we will include an LCD display. We create a script in Python using the packages needed to the LCD display this way. This display can only show up to 32 characters, which should be enough for what we want to show on the display itself. The current plan is to only show the user on this display previous feeding time and upcoming time. 32 characters, enough to show that much. Lastly, in terms of software, we will be talking about remote communication, access, and logging. Currently, what we have planned for our app is that it has a lot of moving parts, and we need to communicate with the Raspberry Pi because we're asking the. We also have given the user the option current feeder status and past feedings as well. Need somewhere to store all of that information, and that also includes the set feeding times that the user. So, Flask framework to host a web app, store all of that data. In terms of organizing an MySQL database, open source database, we can easily set it up to where all the information organized.
All right, let's go over some of the technical challenges associated with this project. So first off, on the hardware side of things, we have to consider the fact that we have a good number of hardware devices that we're trying to incorporate into this design. So we want to make sure that all of them basically play nicely together. And with the I2C protocol that the bonnets use to communicate shouldn't be an issue. Another thing we have to consider is power management. So for example, the PWM bonnet needs 5 volts to operate, while the stepper motor one needs 12 volts to operate. And our Pi needs 5 volts, 3 amps to operate as well. So we have to make sure that all of the different hardware devices get the proper amount of power they need. In addition, when we get closer to the final design of the project, we have to make sure if heat is an issue, if any of the hardware components generate any significant amount of heat, we want to make sure that that's taken care of with a fan or cooling vents or whatever needs to happen. On the software side, we have to consider security. So we want to make sure that not just anybody can log in, tap into your camera's live feed or feed your cat or anything nefarious like that. Also, we have to consider that the device needs a Wi-Fi connection to operate. So, for example, when you first get the product, if it were a real product, how would you set that up? So we could do that potentially over Bluetooth or something. Access to information. So we want to make sure we want the app, the user, to be able to see some information even if the Pi or the unit itself is down. So for example, that would be like the feeding log and your schedule and stuff like that. Also, remote communication is something we're going to have to figure out. We want to be able to not only remotely communicate with the device from on the same network, but also anywhere in the world, potentially. Also, there's just a lot of unforeseen challenges that come along with software development. It's just something that always happens, so we have to prepare for that. So for work distribution, the way that we're gonna split it up is we're gonna have Carlina be doing a lot of the hardware aspects, while Bradley and I take care of a lot of the software aspects. But of course, we will all be kind of participating in all different aspects of putting the project together and whatnot. But we're gonna have Carlina work on 3D modeling the final design for the project. She's gonna help me hook up all of the different hardware components when we get all those, make sure those are all working, and then just overall design the product, make sure everything looks nice, and also, of course, contribute with the software. So on that front, Bradley and I will be doing that mostly. So Bradley will be working on the mobile application and figuring out the software to communicate with the Pi camera, while I will be creating the Flask web app on the Pi, figuring out how to host the server on it, things like that. And then once we'll kind of merge later once we've got those things set up, Bradley and I, and work together on the mobile app. So here are the materials that we'll be needing for the project. I won't list off all of the things here, but some of the highlights would be the stepper motor, the bonnet to drive it, the PWM motors and the bonnets to drive those, and the laser, of course, the Pi, the Raspberry Pi, the LCD screen, and the power supply for all of that. Okay, and here's our timeline. So the first week we plan to, of course, order all of our parts, and Bradley and I will start working on the interface for the mobile app, as well as me. I will start figuring out how to host the server using Apache and Flask on the Raspberry Pi. And then going to the next week, we will start testing all of our parts, getting our circuitry done, and getting the code done for all of the different hardware components, which will also be done in Python. And then the next week, we will be testing the simple prototype, getting the functionality of the motor and all that hammered down, and trying to test the prototype's functionality with the app, the mobile app.